Alright, so we're back with the final video on tiling chessboards with L-Trominoes, and so we're looking now at even n by n boards, and I think we're actually going to make a very small piece of history here today. And the last scene of this video, we've got a 50 by 50 board, which is what we've been building up to across all of these videos, actually tiled explicitly with these L-Trominoes, deficiently as well. So one square is missing, but that's sort of what we've been trying to investigate. So yeah, I think it's fascinating. I don't think anyone's ever actually maybe shown a 50 by 50 board tiled efficiently with L-Trominoes. It's been proven that it can be done, which is what we're going to talk about, but has anyone actually done it? Maybe not. So maybe if you're really interested, you can just skip to the end, and if that's all you want to see, then more power to you. Go and suss it out. But yeah, if you want to hang around and think about, how it happened and how we get there, let's look at this. So recap from the previous videos, I'll put a link below. Basically, hopefully by now you're aware that L-Trominoes are these sort of L-shaped unit squares. So you've got 3 unit squares in a sort of L shape. You can rotate them however you like, so there's 4 different rotations. A deficient n by n board has exactly 1 square removed. So that's what we're sort of looking at today. And some of the propositions we learnt and theorems we learnt from the previous videos is that a 2i by 3j rectangle tiles completely. So that just means if your rows and columns in your sort of rectangle are a multiple of 2 and 3, then you can tile that completely with L-Trominoes, and that's very easy to show. And from our previous video, this was less easy to show, is that the theorem says that if n is odd, greater than 5, and not divisible by 3, then any deficient n by n board tiles with L-Trominoes. So this is all from Chu and Johnson Bowers' 1986 paper. So full credit to them for obviously doing all this stuff, fascinating recreational sort of mathematics. If you want access to that paper, or you want to be pointed in the right direction so you can just get on with it and don't have to hear me talk, then just reach out and I can point you in the right direction. But yeah, today's video is about n being even and not divisible by 3, and particularly n equals 50, because that's what we've spoken about in previous videos, and that's what we've been trying to build up to. So stick around. If you are finding these videos interesting, give us a thumbs up, all that fun stuff they do on YouTube. Subscribe so we can keep the good times going. If there's certain problems you want me to look at as well, just let me know, because I like sinking my teeth into interesting problems. So here we go. Let's talk about just this idea of when can a deficient n by n board tile. So this is obviously a condition we have to have, right? For it to be deficient, or even to be tiled deficiently, which means 1 square missing, right? We need n squared minus 1 squares to be covered. So let's just think of an example. So, if n was 7, so 7 by 7, so 7 squared is 49, minus 1 is 48. 48 is divisible by 3. So, it's in the realm of possibility that it could be tiled deficiently with L-Trominoes. And so, yeah, we can say that we need n squared minus 1 to be divisible by 3. And this is true as if and only if, that's what this sort of backwards arrow means, n is not divisible by 3. So let's just give an example here. So if n was divisible by 3, so let's pick a number like 6. 6 times 6 is 36. 36 minus 1 is 35, and 35 is not divisible by 3. So we wouldn't be interested in a 6 by 6 board in this sort of situation, because it wouldn't be tiled deficiently. It can either be tiled entirely, or maybe it can't be tiled entirely, but we're not interested in that situation. So hopefully that makes a little bit of sense. And just some sort of key information here, which we're calling proposition 1, which is that the cases n equals 2, 4, and 8 can be tiled deficiently. And over here we've got a 4 by 4, which we can clearly see is tiled deficiently because there's 1 square missing, and we've spoken about this before, but a 4 by 4 can be tiled with any square missing. And importantly, for the proof that we're going to do, for an n by n, where n is even and not divisible by 3 and greater than 8, we're going to say that the top left-hand corner could be missing. And you can clearly see that through rotation. But just interestingly, a 4 by 4 can have the missing square in any position. So we just need to hold on to that information that, a 4 by 4 can be tiled efficiently, and an 8 by 8 for that matter, but 4 by 4 is more important for this video. Okay, this is almost going without saying, hopefully, at this point. But again, if you've got multiples, rows and columns that are multiples of 2 and 3, a row number and a column number that are multiples of 2 and 3, then you can have you can tile it completely. So like a 6 by 6 can be fully tiled. And yeah, I know the colors can look a little bit confusing here, but just pause and I guarantee you that if you look long enough, you can see where the Trominoes sort of fit together. And yeah, you'll be able to see that this tiles completely for a 6 by 6, because clearly we have a row number of 6 and a column number of 6, and that is a combination that's allowable because it's in the form 2i by 3j, because 6 is obviously a multiple of 2 and of 3, so that works out fine. And that's important for our proof as well, so hold on to that, because we're going to get these little rectangular strips that we need to be able to tile completely. So let's look at the proof, holding on to those two pieces of information. So this is the famous proof, or maybe not so famous, but here is our sort of example diagram here. So we're looking again at n greater than 8 and not divisible by 3. And so if we just look at the 10 by 10, that 10 probably jumps out as the number that first comes to mind when you think about numbers greater than 8 and not divisible by 3. So let's see how you would decompose and create your diagram. So you've got 10 by 10. So what we're going to do is, one thing we could do is say, all right, the top left, we're going to have a 7 by 7, which we know can be tiled deficiently because that's what theorem 1 said, because that's odd, and that's fine. We can tile that deficiently, so we have 1 square missing there. In the 4 by 4, in the bottom right, we just showed that that can be tiled deficiently as well. So if the removed corner was in that junction sort of cell, then we could have a situation where we have our missing square somewhere in the 7 by 7, and then this sort of junction cell would be filled by some other part of a Tromino in the 7 by 7. And yeah, then that would be fine. And then we would have the 6 by 3 and the 3 by 6 that can be tiled completely with L-Trominoes. So those yellow sections can be tiled completely. So we know that can be done. And we know that the blue and the green sections can be tiled deficiently, but together they can work together such that you have just a missing square in the top left in the 7 by 7. And then obviously through any rotations of that, you could have the missing square being in any part of the board, which is interesting. And that's really what we've shown here. And yeah, if we just sort of talk more generally now, well, we looked at a 10 by 10. Well, what did we do? We said 10 by 10 became 7 by 7 in the top left. So essentially we're going to say, all right, now we've just got n by n. So what we're going to do is we're going to take n minus 3 by n minus 3 as that top left sort of larger, in this case, section. And we know that if n is even, like 12 for example, and then we subtract 3, we get an odd number. And so by theorem 1, we know that we know that an odd by an, 9 by 9 or something like that can be tiled deficiently. So through theorem 1, we can see that that blue section can be tiled. The yellow sections, you'll end up with an n minus 4 by 3 and a 3 by n minus 4. Okay, that's going to be done with those sort of rectangular strips that we spoke about, because we've got an n minus 4 by 3, so we've got our multiple of 3 there. But n minus 4, if n is even, which is what we're talking about, if you take an even number and subtract 4, you get an even number. So just pick an example, 16 minus 4 gives you 12. So, and 12 is clearly divisible by 2. And that's the condition we had for those rectangles. We need the n minus, we need that to be the number of rows and columns to be a multiple of 2 and 3. So those yellow strips can be tiled completely. And then we know we're going to end up with a 4 by 4 in the bottom right hand corner, and we know that that can be done deficiently. So we can have our missing square anywhere in that blue section, and then yeah, we know that every deficient n by n board where n is greater than or equal to 8 and not divisible by n is not divisible by 3 can be tiled. And that's it. That's really the essence of what we've been trying to show all this time. Hopefully you can see how the pieces fit together. It's a bit of a pun there, given what we're talking about, but how the pieces of the theorem fit together. because then what we're going to do, now what we're going to do, I should say, is we're going to do the 50 by 50 board, because that fits our criteria, right? Because 50 is even. It's not a multiple of 3. That was our condition as well. And n squared minus 1 is apparently divisible by 3. So 50 squared is obviously a large number. Minus 1 must be divisible by 3, so that we can think about tiling this efficiently. Anyway, so here we go. This is what it would look like in terms of the diagram. So our count is 50 squared minus 1, which is 2,499, which is 3 times 833. So in total, we would need 833 L-Trominoes. And this is the decomposition of our 50 by 50 grid that we would need, that we've got in this diagram here. So we've got a large 47 by 47 that can be tiled efficiently through theorem 1, because that's odd. And then we've got 2 strips of 46 by 3 and 3 by 46. Again, multiples of 2 and 3, so they can be tiled perfectly. And then very small, in this case, 4 by 4, that sort of sits in the bottom right-hand corner. And that is our valid decomposition that shows that a 50 by 50 board can be tiled efficiently using L-Trominoes. So isn't that interesting? Here it is. Drum roll. We need a big drum roll, because we've been building up to this for a while now, and it's taken up a lot of my time. I'm just going to move my face for a second. So let me just... And yeah, so here we have it. Isn't it kind of beautiful? Maybe it is to me, because I've been working on it for quite a while, but there you go. It sort of extended the powers of AI coding to make sure that it got everything right, but maybe just some key features that you might want to look out for. I can't find any errors with it. Seems to me as though it looks pretty good. I know they can get a bit tricky with the colors, but like even up here at the top left, it's green. But you can, everywhere I've looked, you can sort of distinguish the L-Trominoes. If I've made an error, please look at it carefully. But yeah, we can see we've got our big 47 by 47 grid. Down the bottom right, we've got a 4 by 4. And then down these strips here, we've got a 46 by 3 and a 3 by 46. And so, yeah, we've got our deficient tiling. The missing square is in that top left-hand corner there. Hopefully you can see that as well. So yeah, isn't that interesting? It's probably not been done before in terms of actually showing a tile. It's been shown that it can be done, but I think, you know, it's cool to be able to see that specific example. So yeah, hopefully you found that interesting. Give us a thumbs up if you did. Reach out. Always interested to hear what people have to say about these types of things. And yeah, good luck with everything that you're doing. Have a look as well, just in this bottom, at that joining square there, we've got sort of a purple L-Tromino that sort of bridging the gap there for us. So it sort of hopefully makes it a bit clearer. But interesting stuff. So good luck with everything you're doing, and I'll see you soon.